Assalamualaikum and hi to my students. Welcome to another video lecture for the new chapter 4, Proof Techniques. From the previous lesson, we know that logic cannot determine whether any given fact is actually true or not. It just can evaluate arguments, whether those kinds of argument can be valid or invalid. For example, the modus ponens, where they have two arguments and one conclusion. P implies Q. You state P and your conclusion is Q, is proven to be a valid argument. That kind of argument is also known as direct method, which we will learn in the later part of this chapter. Therefore, proving techniques is a great combination with logic. Before we begin, I would like to start first with some preparatory content, which is on how to link the logic chapter with the proving chapter. We start first with the quantifiers, okay, for all and there exists. From the previous video of Madam Anis, we learned this. For all here, and is this there exists, or for some. We put true here and we put false here. This is known as I name it as a metric of logic and proof. Okay. For all thinking, when you want to prove some for all cases to be true, if it is true, then we need to prove all case true. Later I will show you the examples. If the for all statement for all elements is false, you should prove one case is false. You also call this counter example. No space. Counter example. In contrast to for all, for there exists quantifiers, there exists something shown to be true, then you just need to prove one case to be true. And if there exists something which is false, you should prove all case false. In my face-to-face lecture from the previous semester, I would like to highlight this matter as well. Which segment which is the hardest? I show with the simplest one first. To prove for all is false is the easiest. This is the easiest one. To show that there is some case is true, this is the next easiest one, and the next easiest one is true for all, and the hardest one it should be for all cases to be true. Later we will go through the examples. An easy example we start first. We start with this example. Question. Suppose I define a set A which comprises of 3 elements. Okay, 1, 2, 3. This is a small integer. And perhaps I have this statement proof for all elements in set A. This happens, the predicates. X squared is larger than or equal to 1. From the previous table, it states that if we want to prove whether the elements for all elements in the given domain is true, you should show that all cases is true. As this is a finite case, you should show one by one x equals to 1. For example, when x equals to 1, what is 1 squared? What is the x squared? Is 1 squared is 1. And it happens that 1 is larger than 1, therefore true. But we cannot stop here. For all cases, we need to show that every element in this case is true. We proceed with the x2, where x2 squared is 4, and of course 4 is larger than or equal to 1 also happens to be true. When x equals to 3, x squared equals to 9, 9 is larger than or equal to 1, which happens to be true. As my conclusion, I just proven that all x in A, x squared is larger than or equal to 1 is true. This is how we prove for all elements in any given domain to be true. And this is a case for finite set. We go to the next example, a little bit hard, where it states that for all x in a positive integer, x squared is larger than or equal to 1. The difference with the previous example is that this is an infinite set, and for the case of infinite set, it's quite impossible for us to do x equals to 1, 1 squared, x equals to 2, x equals to 3, x equals to 4, x equals to 5, x equals to 100. This is impossible to mention every integer to be shown to be true. For this case, you will find this case, many cases like this in this chapter. We should put, for this kind of example, a general proof, a general statement which defines every characteristics in that infinite set domain. Let me show you the idea on how to incorporate all elements in this case. The idea is like this. There are many ideas on to convince someone whether this given statement is true. Proving is like an art. You must know how to convey your words so that it can convince the audience that statement is actually true. This is my way of proving. You may have your different way of proving, but always remember is that you must show in the case for all of element in the positive integer for this case. This is my idea. I start first with the smallest integer in this domain is 1, and from the previous example we know that if x equals to 1, x squared equals to 1, and of course 1 is larger than 1, so I say it's true. As x equals to 1 is the smallest x in positive integer, for any integer greater than 1, of course x squared is larger than or equal to 1. Convinced yet? I hope so. If I cannot convince you that this statement is true, therefore I need to change the way of my presentation of proving. As this happen is to be true, from my argument, therefore I conclude with this conclusion, it's proven that all x in positive integer, x squared will be larger than or equal to 1. Some points to ponder in this case, example from the previous two examples, including this one, is that we always start with some argument This is the argument part, and this is the conclusion part. The proving always starts with the argument and will close down with a conclusion. We proceed to the next example. We move to the case where for all elements in any given domain is false. By referring to the initial table, we know that we need to prove at least one counterexample. It's different. For example, I let a question like this. I prove for every x in, this time it's an integer, not only positive integer, x squared is larger than or equal to 1. Be sensitive with the domains. If the domains is different, then the question is different. For this case, it includes negative integer and also 0. For every element in which is an integer, it behaves this way. Be careful not to put a wrong counterexample. This is the example. If the counterexample gone wrong, you say that let x equals to, you say negative 1, and you happen to know that x squared will be 1, and you say 1 is larger than 1. Therefore, you say it's true. However, this proof is false because this statement is actually not true. What is the actual counterexample to show that this for every integer the x squared is larger than or equal to 1? So we cannot trust this one. Although this is a true statement, but this is not a correct proof. Actually, if you let x equals to 0, x squared equals to 0, and 0 larger than or equal to 1 is false. You can put it this way, or you can say that 0 is not larger than and or equal to 1. You can put it that way as well, the same meaning. And it happens to be that for every integer x squared is larger than equal to 1 is actually false. Not all. There exists one counterexample to dictate that this statement is false. So as my conclusion show that there is a one false case, this is one counterexample as my conclusion. For every x in integer, x squared larger than equal to 1 is false. This concludes the proof of this statement. We proceed to the next part, which involves the existential quantifier. I want to prove, for example, let's set A equals to 1, 2, 3. And this time I change the predicate. I need to prove there exists some x in this A such that x equals to x squared. From the initial table of logic and proving, if we want to show that the existential quantifier is true, you just need to show one example, one true example. Beware that do not put the wrong example. Can you identify which x that can show a false example? Verify yourself, but right now I want to concentrate on the actual true example. From these three elements, 1, 2, 3, which can support this predicate to be true? The proving starts now. I just let that x equals to 1, x squared equals to 1, and of course 1 equals to 1, and I conclude is that x equals to x squared. For some, therefore it suffices if we just put one true example. This is true. Therefore, my conclusion is that there exists some x in A, x equals to x squared is true. Proven. And let's proceed to the case where there exists x in some domain which states it to be false. Not yet. Let's try to look back at this example. I just want to involve infinite series. The same predicate, but this time I just change it into a integer. There exists an integer such that x equals to x squared. Again, this, although the domain is different, but still this is a true statement. There exists integer such that x equals to x squared, and yes, I can still use this proving. The proving remains the same although the domain is different. Although integer is an infinite set, we can just use one example to show that it's true. And I can choose x equals to 1, and you can also use x equals to 0, because x squared equals to 0 and 0 is equals to 0. You can use 0 as well. Then we proceed to the next example. The next example is about there exists x in an integer, but this time I change the predicate is that x squared is less than 0. I know some of you already happens to know that x squared cannot be less than 0. X squared cannot be negative. Most of you know that. But how to convince the people, how to do the proof part such that we can believe that this statement is actually true? You must show for existential quantifier that all cases is wrong. You must prove that all cases is wrong. In a general term again, because this is infinite set again. This is the hardest way to convince. But the idea is that you must represent your proof such that it represents every integer. We start first. My idea again might be different from yours. I differentiate this case into 3. I start first if x is negative. If x is a negative integer, I let, for example, negative x. Negative x squared is x squared, and it is not less than 0. I put the second case, let x equals to 0. 0 is special because it is neither negative nor positive. 0 squared is 0, and 0 is not less than 0. And lastly, I let x include the positive integer. This one is very easy. X squared, of course, is not less than 0, as you all know the fact. These 3 cases represents every cases in the integer. Therefore, I conclude that it is proven that there does not exist x in integer x squared smaller than 0 is false. Don't worry so much about the representation. Some student might ask this, can I use this, sir? There does not exist x in z x squared less than 0. This is also the same conclusion. You might also no, this is only maybe there are different conclusion that can you make as long it remains the same meaning. So that concludes the preparatory part, the preparation part, which is on how to link the quantifiers with the proving methods, and how we will proceed for the next part of the remaining subtopics in this chapter. The first part is the direct method, of course the introduction, and then the direct method, indirect and contradiction, and lastly is the math induction. Strong induction is included in the math induction as well. Different ways of proving. All of them are logically valid arguments. In the direct method, I will differentiate it into some sub-lectures. For example, I once said in my face-to-face lecture during the pre-COVID era is that if you realize that every chapter start with the number theory, there's a proving part of that. There is a proving part of that. Logic also, you must prove that whether a statement is equivalent or logically valid or invalid. That is also a proving. And of course in chapter 5 there are lots of proving. Proving should be initially in the first chapter, but based on some requests from your faculty, FCOM, they decided to move it into chapter 4 because this chapter is a little bit intimidating. But rest assured, actually proving is fundamental. It is the basic for every mathematics. So it is not hard. It seems hard, but if you understand the thought process and why we need to prove the statements, it actually will be easy. Till we meet again in the next video lecture. Thank you.